In this video, we're going to switch gears and start talking a little bit about covalent compounds. And specifically, we're going to focus first on how we name them, and then we will get more into the structure of the compounds a little bit later. So with ionic compounds, we've been talking a lot about how we can predict the formula, that if we know what ions are involved, if we know what elements are involved, we can just write the formula because there's only one way that they can combine that makes the charges add to zero. The same is not true for covalent compounds, which is why we have a different naming system for them. Because in covalent compounds, the same elements can combine in multiple different ways. And it's not just due to a difference in charge, like the transition metals, where we have sort of a predictable, simple way that we can describe the difference between these two things, that once you know the charge, there's only one option. It's not that predictable. So in covalent compounds, the same elements can combine in multiple different ways. So for example, some compounds that you might be familiar with are CO2 and CO, and you might even know the names of these. CO2 is carbon dioxide, and CO is carbon monoxide. So you'll notice that there's kind of some similarities to what we've been talking about with ionic naming, that we have that "ide" ending still for our last element, but we have this extra piece, that prefix of dioxide versus monoxide, that we're specifying how many oxygens are in these two compounds, that di means two, mono means one, and that's how the difference in the formula is reflected in the name. So we use prefixes to specify how many of each element are present in the formula. So we use the prefix mono for 1, di for 2, tri for 3, tetra for 4, might be a little different than what you're used to, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10, and again, that's about as far as you should ever really need to go. So we add a prefix to each element with kind of one little caveat to indicate how many there are. So the one little asterisk to put on this is with mono. The prefix mono is only used on the second element in the compound, never on the first. So otherwise, we put prefixes on both. There's a prefix on the first and the second in most compounds if there are multiple atoms of both. So that's kind of the one exception to that. So the prefix mono is never used on the first element in the compound, that it's sort of just implied if there's no prefix on the first one that it's only one of that thing. So this is where, kind of go back to these names are coming from that you might be familiar with already. CO2, you likely know, is carbon dioxide. So you'll notice that we did not put the prefix mono on the first element, on the carbon. There's only one carbon, but we don't specify that. If there were two, we would say dicarbon. We'll do some examples like that in a sec. But since there are two oxygens, we put dioxide. For this guy, we call this carbon monoxide. So we are including that prefix of mono on the second element to indicate specifically that there is only one oxygen in this formula. So that's kind of how these names are being constructed. So let's look at some more examples. So let us provide the names. For these two compounds. So see if you can pause here and give these two a try on your own before I do them for you. Cool. So the first one, NO2, very similar to CO2. We're going to name the first element, including any appropriate prefix. There is only one nitrogen, so we do not include the prefix mono. And then we have two oxygens, so we use the prefix di. And we do still end the last element with that IDE ending, so nitrogen dioxide is correct here. For the second one, we have two nitrogens, so we need to include a prefix. If it is anything other than one, we include a prefix on the first element. So to specify that there are two, we would call this dinitrogen. And then there are 5 oxygens. So this would be dinitrogen pentoxide. Note that the A frequently gets dropped from these prefixes. We don't double up on vowels. So pentoxide is weird to say, so we drop the A and kind of elide it together to get pentoxide. I don't penalize for spelling, so if you left the A in there, that's totally fine. Again, that's the kind of nuance that comes with experience and being like, yeah, pentoxide feels weird to say, pentoxide feels much nicer. That you just kind of get from intuition eventually. We can go in the other direction, and that's very easy. If we're given the names, we can provide the formulas. So let's try dihydrogen monoxide and arsenic triiodide. So pause here, give those a try, see if you can parse out what the formulas are based on those names, using the prefixes to indicate how many of each element are present. So in the first one, we have dihydrogen. Di means two. So that is telling us there are 2 hydrogens, so we'll have a subscript of 2 after H in our formula. And monoxide is telling us that there is 1 oxygen, so we will not have a subscript, we'll have an invisible one after the oxygen. So dihydrogen monoxide is technically the chemical name for water. And then arsenic triiodide, no prefix on the first element tells us that there is only one of those. Remember, we drop the mono if there's only one for the first element, and then triiodide, this is a case where we actually do double up on the vowel, is telling us that there are 3 iodine atoms in that formula, so that would be AsI3. So by adding in these prefixes to our naming structure for covalent compounds, this is helping us distinguish between different ways that the same elements can combine. If we didn't include those prefixes, we'd have no way to distinguish between these two compounds. And there are loads of other nitrogen-oxygen compounds as well. So remember that the prefixes are telling you how many atoms, and this only applies to covalent compounds. We never use prefixes for ionic compounds.